Hi guys, in today's video we're going to be looking at motion where we have both rotation and translation. So particularly we're going to be worried about the case where we have rolling with and without slipping. So today the scenario we'll have a bowling ball which will be rolling along a surface. So it's going to have some velocity and we'll call that v center of mass. So it's going to have some linear velocity to the right and it's going to have some rotation about its center of mass as well. So in order to figure out the condition for this to be rolling with or without slipping, we have to recall what that means. And basically, if it's rolling without slipping, that means that this contact point of the object and the ground is at rest without slipping. And if it's slipping, there's going to be some relative motion between this contact point and the ground. So that's going to be what we want to look for. And so we can derive the condition that we need in order for this to be rolling without slipping, which we'll use today. And we do that by recalling that this motion is a sum of translational and rotational. So we can draw here just the translational motion, which is to say that when we're translating, we're mostly going to be concerned with this point of contact. So that point of contact is going to have some velocity, center of mass. That's just the translational motion that this whole bowling ball has to the right. And similarly, we're going to have some rotational motion. So you'll recall when we have this rotational portion, we're only worried about sort of these velocities, which are tangential to our rotation. And so in this case, again, we're concerned with the point of contact with the ground. We're going to have our tangential velocity from our rotation alone, and then our translational velocity from the ball's motion, its linear motion. And so then our condition for rolling without slipping is just to say we want this point of contact to be at rest. So therefore, our center of mass velocity must be equal and opposite to our tangential velocity. So that gives us sort of a form here. We know our tangential velocity from rotation is always equal to omega r. And so that's just to say whatever omega this is rotating with, that will give us some tangential velocity by multiplying it with r. And then we can set these two equal and get our final relation, which is to say our v center of mass must be equal to our v tangential, so that these cancel out. They must be equal and opposite. And therefore our relation is that our v center of mass should just be equal to omega r. So we'll use this today. So let's go ahead and read the problem statement. A bowling ball of mass m and radius r is released from a floor level so that at release it is moving horizontally with a speed v0 is equal to 5 meters per second and is skidding, not rotating. The coefficient of static friction μs is 0.1 and the coefficient of kinetic friction μk is 0.08. Find the time for which the ball skids on the floor, after which it starts rolling without slipping. At this point, you should pause the video, reread this problem a couple times, and maybe even try it on your own. Okay, so we have our scenario drawn out over here. And so in this case, the scenario itself is fairly straightforward. We have a bowling ball which has been thrown, and it is going to contact the ground. So it's going to be rolling, and it'll start out by skidding, which means that it's rolling with slipping. And then eventually this will become motion where it's rolling without slipping. So what we want to find is that transition point. We want to find how long does it take to transition to rolling without slipping. So our first step will be to recall our condition for rolling without slipping, which is just velocity of center of mass should be equal to omega times r. So this is what we want to meet, and we want to find the point in time where this is true. So in this case, this sort of gives us a hint as to what we want to be looking for. So we want to basically find the velocity of the center of mass of this object and its omega. So we can go ahead and start by drawing our free body diagram. And in this case, that is fairly straightforward because we only have one force. So in this case, as this ball is rolling with slipping, so as it's skidding, which is the time period that we're looking at, it's going to have some kinetic friction force, which will just be opposing our motion, so it's to the left. And so in this case, that'll be the only force acting. So at this point, we want to decide what is that going to do to our quantities of interest, and how is that going to help us meet this criteria. So first of all, we start with some v center of mass. So it starts with some initial translational velocity, and it starts with no omega. So the omega starts at 0. And the reason is it's released level to the ground. So it starts not spinning. And so what that means is this equation, of course, cannot hold right away because we start with some VCM, some V center of mass, but we start with 0 omega. So this right side is 0 and the left side is not 0. So that's good. I mean, that just means that we start by slipping, which is what we're told in the problem. But now we want to see what is this friction force going to do. So for our linear motion, we have a good idea of what this force will do, right? The force is just going to work. It opposes the motion, so it's just going to give us some negative acceleration, which is to say our center of mass velocity is going to be decreasing due to this frictional force. But now the other important thing to know is also this omega will be changing because of this force. And so that is because anytime you apply a force away from the center of mass, and if it's perpendicular to the radius that you apply it at, then you're going to have some torque, right? And so in this case, we see we have a direct torque due to this frictional force that's going to work to rotate this object here. And so therefore, our omega will go from 0, but it will be increasing with time. So this frictional force is a torque. It's going to increase our omega. And so this is the changes that we're going to see throughout time. And so we see this is good because this can actually allow us to get to a point in time where the relation holds. So our velocity of center of mass starts at some value, and it's going to decrease. And then our omega is going to start from 0 and increase. So eventually there'll be a time where they meet in the middle. And then this condition holds, and that is the time that we want to solve for. That's when it's going to transition to rolling without slipping. So that's sort of the game we want to play here. And you should go ahead and pause your video and maybe with this in mind see if you can solve the problem now. But our next step is going to basically be we want to find our V center of mass with respect to time and our omega with respect to time. So if we can find these quantities at any given time, we can set this equal to this relation up here. We can set VCM equals omega r and then solve that for the time. So our first step is going to be to look at our linear motion. And so for that, I'm going to use the color green. And for our linear motion, we have something we've dealt with a lot before. So we're going to look first at our kinematics, which is just to say our VCM is always going to be equal to our initial velocity. So in this case, that's 5 meters per second. And then this is just plus acceleration times time. So this is just our equation of motion that we know is true. And this sort of gives us an equation for the velocity at any given time. We just need to solve for our acceleration. And so in this case, our acceleration is due entirely to our frictional force. So that means that we know by Newton's second law, the sum of the forces on an object is the mass times the acceleration. And in this case, our sum of forces is just the frictional force. So basically, we're going to have frictional force is equal to ma. So that's to say this will break down, become force of kinetic friction. And we also know the form of the kinetic friction force, right? First of all, let's recall it's negative. So I'm going to go ahead and put that in. So it's going to be negative mu k times mg. So this mg is just our normal force. So this is something we should be comfortable with at this point. And basically, we just want to set that equal to ma to satisfy Newton's second law. So we can see our masses cancel, and we find that we now have a relation for our acceleration. At any given time, it's just going to be mu k times g. So it'll be a constant negative acceleration. So we can plug that acceleration in up here and get our first relation that we're looking for. So that's to say, if we do that, we should get velocity center of mass is equal to v naught, which is a quantity that we know. It's 5 meters per second, minus mu k times g times time. And that is just from this top equation here. So I'm going to go ahead and box this because this is a very important result. This is really 1/2 of what we're looking for. And then we know at the end we're just going to apply this condition. So now to get our second half, to get our omega, we know we're going to have to look at rotational dynamics. So we're going to really follow the same steps, but now everything will be the rotational analog. So in this case, instead of v equals v naught plus at, we will have omega is equal to omega naught plus alpha times time. So this is the same equation in rotational form, and we're going to do the same thing. We're going to look at Newton's second law in rotational form, which is to say the sum of our torques is I alpha. So this is Newton's second law in rotational form, And the only extra step we have here is that we have to recall our torque is not just the force. Our torque now, and I'll write this over here, our torque is always going to be equal to R cross F. So this torque is a vector, R and F are vectors. So we can solve for this just by looking at our free body diagram here. We see that we are applying some force away from the center of mass, so it's going to have some torque. This here will be our R vector. And so in this case then, our torque is just going to be our radius times our force of friction. So that's to say, let's go back to the correct color, that's to say this torque is just R times force of kinetic friction. And again, we're going to impose that that must be equal to I, which we're told is 2/5 mr squared, and then times alpha. So everything else is the same here. We have our m, we have our force of friction is the same. It's going to be mu k times mg. So we can plug all of this in, and we can just solve this directly for alpha. So go ahead and follow along in your solutions at home, but you should get an alpha, which will be 5 times mu k g all over 2r. And so once we have this alpha, similarly to over here, we'll plug that into the top, and we know our omega naught is 0. It starts with no rotation. So our omega as a function of time is just this alpha times time. So finally we have our second part of this relation here, which is to say omega should be equal to 5 mu k g over 2r, all of that times time. So here we now have our two relations, and all we now need to do is impose this rolling without slipping condition, and then we can solve for our time. Everything else here are knowns, so basically we're going to set this equal to this times radius, and then solve for time. So you guys can go ahead and follow along in your solutions at home, but that allows us to find the answer, which says our time until it rolls without slipping should be 1.8 seconds. So that's to say, in 1.8 seconds after you throw the bowling ball, it's going to start its rolling without slipping motion. So let's go ahead and review what we've just done. First, we recalled our condition for rolling without slipping. Then we looked at our linear motion to solve Newton's second law for the center of mass velocity with time. Next, we looked at our rotational motion and solved for the angular velocity with time. Then we set these equal with our relation for rolling without slipping, and we found our transition point for time. Okay, so I hope this video was helpful, and I hope it clarified some points about rolling with and without slipping. So if you guys have any comments on any of these videos, please leave those to the link to the right of the video link on TED. Thanks for watching.